I am Anil Kumar. Welcome to the series with Aryan, grade 8 student doing grade 11 mathematics. We'll study probability and understand foundations and concepts. Share the passion of learning, stay ahead of competition, give the gift of education. Ignite the spark of learning. Join Anil Kumar classes. In this video, we'll learn probability, understand tree diagrams, Venn diagrams, inclusion and exclusion principles, dependent independent events, along with conditional probability. Let us enjoy the lesson with
Hi,
Aryan.
Aryan. How are you doing?
Hi, sir. I'm doing good. How are you?
Very good, very good. Yes. So far, what kind of marks are you getting in maths?
So for the midterm that I took, like the other day, I got a 93 on it.
90,
Yeah, and
90 plus is excellent. You know, that is very good. So congratulations for that. Now, what do you want to do?
yeah. So I would like to to start like the basics of probability
Correct.
as like a subtopic, kind of.
Perfect. So you have chosen the right topic. So in grade 8, you're thinking about probability, and definitely it is not that hitting a target and like what are the
Yeah,
chances of getting spinner on 6 or 7. Well, straight away jump to a high level of probability, working out the probability of events, right? So
yeah,
I would like to begin with very basic concepts, and based on that we are going to build upon, and we will see how to actually solve very difficult questions based on probability from these simple concepts, right? That's the whole idea of today's class.
okay.
Right? So I'll just share a whiteboard with you and then we'll talk about probability. Can you see my screen?
Yeah, I can see it.
Okay. So a few terms which are very important for us to understand are in a probability thing, we are talking always about an event.
Yeah,
So whenever you say a probability of this, so this is an event, correct? So you have to define the event very clearly, right? So first
yeah,
step is to have clear idea of what is the event whose probability you want to find. Okay? So event normally will be written with a capital letter, let's say some letter A. And we define the event as, let us say we are playing with a dice. Dice is a very simple and good example. We are playing with
yeah,
the dice, and what we say is the event is to get a prime number.
yeah,
So we have defined an event, and this is to get a prime number. So whenever we are looking for something, to get a prime number means if you get a prime number, it is success. So if you get, then it is a success. Otherwise, it's a failure. Okay.
okay.
So it is always between yes or no, true or false. That is a clear cut answer, right?
Yeah,
So when you throw a dice, in that case, we are looking into what are all the events, outcomes of the events, right? So let's say this is our dice. So we use a word that this is a fair die. So it is fair die. Fair dice basically means that probability of getting, I'm using the word probability, the chances of probability of getting 1 to 6 any number is exactly same, right? So for example, this dice has, let us say these numbers, right? Let's say. So we say if you throw the dice, what can come as an outcome? We call that as an outcome, right? So we say that the outcome could be these numbers 1, 2, 3, 4, 5, 6, right? That is my outcome. Correct? So when we say this is my outcome, we are actually interested in number of outcomes. So we will
Yeah.
write that number of outcomes is how much. So we say there are 6 numbers which are possible. 1 to 6. You get the idea.
Yeah.
So number of outcomes. So these are total number of outcomes. We'll call this as a sample space, right? So we use the word S for sample space for now. Okay.
Okay.
So that is the sample space. We are saying number of outcomes, total number of outcomes in our experiment. So when you throw this dice, this is called an experiment.
Yeah.
So those are the outcomes. Now, when we are looking at a prime number, then that becomes our favorable items, right? So win position, correct? So we say, so what is the outcome of getting A? A is my event, right?
Yeah.
So out of these, what are the prime numbers? Well, the prime numbers are only 2, 3, and 5. So we have three prime numbers, right? So when
Yeah.
I put them in the curly brackets, I'm listing out the prime numbers. I should not have written an A here. And A will be the number of successes, which is 3 in this case, right?
Yeah.
1, 2, and 3. But these are the the favorable outcomes, I should say, right?
Yeah.
And as you know, probability basically is of the event A will basically be the ratio of favorable to total number of outcomes. Is that clear to you?
Yeah.
So in this case, it is half, 50% or half. So probability can be always written in a fraction or as a decimal number or as a percent. Right?
Okay.
So you could write this as this or 0.5 or you can say 50% as you wish, depending on the situation. So that is the basic. So what we have learned here is that to find probability, we define an event. So we are finding probability of an event. We should know what are the total outcomes of that event. We should know the success criteria, right? So once we know the success criteria, we'll figure out the in numbers, what are the total number of outcomes and what are the total number of ways that you get a success. Their ratio becomes the probability of that particular event. Now, I use the word experiment. Sometimes we experiment and find the probability of an event. If you are doing experiment, then you have to do large number of times. We'll say almost infinitely large number of times, right? So very large number of times. The event has to be repeated large number of times. This is critical. If I just perform experiment for 25 throws and say, oh, well, in my 25 throws, I got 6 5 times, and therefore the probability of getting 6 is 5 over 25, it will not be considered to be a right result, right? Because the number of times the trial was done was not sufficient enough to give you the result. Is that clear to you?
Yeah. Yeah.
But most of the time, we'll be working with theoretical probability, in which we will assume things are fair. We know exactly how many chances are there, kind of. I mean, and then we work it out. Is that clear to you?
Yeah. Yeah.
And there are other kinds of probabilities also where we could get the data from somewhere and get, but we're not getting there. You understand the basics of probability now, right?
Yeah. Yeah.
Okay, so let's move forward. Now, I will introduce you Venn diagrams. You know Venn diagrams, right?
Yeah. Yeah.
So, let us say Venn diagrams are kind of important when we have more than one event, right? So we have, let us say, more than one event. Let's say 2 events. So single event, it is very simple. You find number of chances, it is going to total number and favorable, find the ratio, get the result, right? Now, when
Yeah.
there are 2 events, in that case, uh, we sometimes get confused and we have to clear that confusion. And I prefer to use Venn diagrams for that. To give you an idea, let us say we have an event, we'll say 2 events, and we say, well, we are playing with let's say playing cards. You understand playing cards, right? A
Yeah,
deck.
yeah,
How many cards are there?
yeah.
How many cards are there in a deck? Do you know?
I actually don't know.
52. You should know. Many
Oh, okay, okay.
students do not know, right? So there are
Yeah,
52 cards, correct? So they are in four suits or colors, right? Suits, right? So they are,
yeah,
you can say heart,
yeah,
spades, diamonds, and clubs,
yeah,
right? So four suits. And each suit, 13 of each.
yeah,
In 13 of each, you have an ace, right? So you have an ace. I'm not writing one for it, but ace, and then the numbers 2, 3, 4 to 10, right? And then the face cards, Jack, Queen, and King, right? So these three are called the face cards. Correct. Now, ace is could be considered as one, and ace could also be considered higher than king. So ace can fit at both the places, right? So when we say a sequence, in this case, ace 2, 3 is numbers in a sequence, right?
yeah,
Ace, king, queen is also a sequence. You get the idea. Ace,
yeah,
king, queen will also be a sequence, right? So in playing cards, we have number of combinations, right? Because there is a lot of variety. There are four suits, 13 cards of each type. So 4 times 13 is 52. And face cards and aces and these numbers with us, right? So this is what a deck will look like. Okay.
yeah,
Now, when I took the example of a deck, let's take some examples now. So what is the probability? So I'm writing probability P and the event in the brackets. What is the probability of drawing a red card? Tell me. We're talking about a fair deck of 52 cards. Is that okay?
okay.
So what is the probability of drawing a red card? So two of them suits, which are hearts and diamonds, are red, and clubs and spades are black. Correct?
Okay.
So when I say so, red cards is uh, hearts and diamonds. So these are the red cards which we look at. Is that okay? So
Yeah,
50% are there. There are 26 out of total of 52 or 26. I wanted to write, right? 26 out of 52, and that makes it half. The okay. Sorry, this is not the shape. Something like this. Okay, and clubs.
yeah,
So, so those are the spades and clubs, right? So,
yeah,
okay. So basically, these are black and these are red. So when I say red, 50% are red. Okay. So we get this. Now, I could say, what is the probability of picking a card which is a face card? Can you tell me that now? So king, queen, and jack are the three face cards. And definitely, total number of cards is 52, right? So that 52 is going to come in the denominator. Perfect.
yeah,
Now, in the numerator, success criteria is to pull out a face card. So there are 3 times 4, right? 12
yeah,
face cards, correct? Because in every suit, there are these 3 face cards. So that becomes the probability of getting a face card. So in probability, you have to reduce them to the lowest terms and then write down your answer, right? So dividing by um, uh, 4, you get what? 13, right? So
yeah,
when 4 players are playing, every player gets 13 cards. So that is 52 times 4 is 13. I mean, 13 times 4 is 52
yeah, yeah,
is something which you always remember, right? And 3 over. Correct. So that becomes the probability of drawing a face card. Now, when we are just doing one operation at a time, it's kind of simple, right? We have 52 cards and you just pull out one, right?
Yeah.
Now, let us now look into the condition when we pull out two cards, not just one card. Is it okay?
Yeah. That's fine.
Okay. So let me clear this. So we have now a probability of getting we have a probability of first I pull out one card and do not replace. So now we could do two things. We could do replacement or do not replace. So those are some problems which are very important to look into, right? For
Yeah.
example, let me see what is the probability of getting, let us say, two aces. When I draw one card at a time. So two aces, and we have one card at a time. Is it okay?
Yeah.
Now, in that case, I could do with replacement. I can do without replacement. You get the idea.
Yeah.
Right. So let's go with replacement. Replacement means I have drawn a card. Whatever card I've drawn, I'll put it back in the deck and then pull out the next card. You get the idea?
Yeah.
Right. So now the question is, what is the probability of getting two aces? That means if I draw a card, it is an ace. Now there are only four aces, right? So there are four aces and 52 cards, correct? So drawing an ace in the first shot is 4 out of 52, correct? Now, whatever card I've drawn, if I put it back, that is called replacement. Again, the deck has the same 52 cards, correct?
Yeah.
Again, we shuffle it properly. So the word shuffling comes very much. Always it has to be shuffled and blindly drawn or randomly drawn. So those words are there. I'm not using them, but they are always there. Is it okay?
Yeah.
If I again draw, again the probability is 4 over 52. Is that clear to you? Correct?
Yeah.
Because same thing. So probability of getting two aces when we are drawing one by one is product of these two. You see, it is very remote chance of getting two aces, correct? 4 out
Yeah.
of 52, you get the first ace and then you draw, again get an ace. So it is an and operation, right? One after the other, you have to be successful. And there are very less chances of doing so. When you multiply fractions, you understand the number decreases, correct?
Yeah.
So we multiply this, correct? We also call this event as an independent event.
Okay.
Very important definition. It is an independent event since the probability of the following event did not change. You see, it remains the same, 4 over 52, right? I'm
Yeah.
not purposely reducing them to lower terms. We are not doing calculations. Here we are only understanding the concepts. Perfect?
Yeah.
Okay. So that is, but if we do not replace, then what happens? Can you tell me, Ryan, what is the probability of getting two aces if we are not replacing? Draw one. What is the probability of getting an ace? 4 over 52. Now, drawing the second as an ace, what is the probability? Tell me.
Um, I know that isn't it the denominator 51 and
Yes.
just yeah.
So it is 51. And now the problem here is we really don't know that in the first case, did we draw an ace? Right. Because if the card which was drawn is an ace, then the number of aces have become 3. Do you see that?
Yeah.
But if the first card drawn was not an ace, then there are still 4 aces there. So now you get confused whether it should be 3 over 51 or 4 over 51. You get the idea?
Yeah.
Correct. So this is a very big question to look into. And many times we get stuck into these positions, right? Today we are not learning a lot of strategies, but we are trying to understand what we should know so that we move forward when we get stuck in such positions. That is the idea of today's class. Is that clear to you?
Yeah.
So we have learned one thing here, that if it is, so definitely this is a dependent event, right?
Yeah.
Now it is dependent on what happened earlier. And the probability of the second has changed. It is not remaining same throughout our experiment, correct?
Yeah.
Now, when you come across such a situation, if this scenario is still simple, we can actually take care of tree diagram. Because tree diagram tells you if this, then that, if this, then that. You get the idea.
Yeah.
So we'll now go through a tree diagram. So these are basic tools which will help you to find the probability.
Yeah.
Okay, so let's continue with our example, and we say, well, we are trying to figure out probability of getting an ace. Now there are two things possible in the first draw, and it is without replacement, right?
Yeah.
Okay, so in the first draw, let us say you get an ace. It is a success, right? You
Yeah.
get an ace. That means, well, the probability definitely was 4 over 52, correct?
52. Yeah.
So, and if you did not get, even then, the probability was 4 over 52, correct? But here we get it, yes, yes, and this is no. Is that okay?
Yeah.
Or let me write, let's write ace or not ace. So I'm going to use a traditional way of writing so that it is good for you. So we are saying we get an ace and we do not get an ace. That means A prime. You get the idea.
Okay.
A
Yeah.
prime can be written as this or with a prime bar. Is it okay? But
Yeah.
the probability of this event remains as 4 out of 52. Now
Yeah.
again, we are trying to see what happens this time. If you have already drawn an ace, and that means there are only 3 aces now left, right?
Yeah.
So getting an ace, oh sorry, this is not 4 over 52, 4, this is 52 minus 4 is 48, right?
Yeah. Yeah.
Right, sorry. So
Yes.
getting an ace is 4 out of 52, but not getting an ace is 4 minus, right? So complement. So this actually gives you complement. So this is another way of writing. So we say 1 minus A, right? So I should not write A. Probability A I should write, right? So, okay. So, okay. So we're mixing up. Okay. Anyway,
Okay.
now getting an A again really means that there are only 3 A's, right? And we have 51 cards left for us. Now, in this particular case, not getting an A will be that there are, what do you say, 51
51.
minus 3. How many? 48, right?
48. Yeah.
48. Now, in this case, you could get an ace. So, if you get an ace, in that case, there are still 4 aces out of 51. And here we have 4 less, right, out of 51. So, if you take away, there are 4 aces, the other numbers are 47. Is it okay?
Yeah.
47 over 51. So, in this case, uh, there are 3 aces out of 51 and 48 are the other cards since we have drawn earlier an ace. Does it make sense to you, right?
Yeah.
So every time we are getting, so this is an ace with us and this is not an ace. Is that clear to you?
Okay. Yeah.
Now, basically what we see here is that this output here is double A, right? So that means they get multiplied and we have a result which is 4 over 52 times 3 over 51. Is that okay? So
Yeah.
both aces you're only getting if and only if first was also an ace, right? You get the idea? So the
Yeah.
next one, 3 over 51. Now, in this case, the output is A bar. In this case, the output is not A's, but A's second time. In this case, not A's and not A's. Is that okay? But
Okay.
multiplying the numbers which come on these paths will give you the probability, correct? So, in this case, it is, you see, 4 over 52 times 48 over 51 is the probability of getting A's in the first chance, but not A's in the second chance, right?
Okay.
And here
Okay.
we have 48 over 52 times 4 over 51, and this is 48 over 52 times 47 over 51, right? Okay. Now, when you make a tree chart, there are many questions which you can now answer. You could answer a question that you are drawing two cards, one after the other. What is the probability of getting the second ace? You see that?
Yeah.
So, if I tell you what is the probability of getting the second ace, so that means we have this in which second ace is there and this, correct? They add
Yeah.
up. They add up, right? You could get the second ace when the first drawn was an ace or was not an ace. Either case, you could have got the second ace, correct? But the path followed gives you the probability. And so, your question, like without replacement,
Yeah.
we are looking for probability of second ace. Do you understand?
Yeah.
So we don't know what was the first card, but we want to know what is the probability of second time when you pick it is an ace. You get the idea.
Okay.
Then you are going to add these two and you say, well, this is 4 over 52 times 3 over 51 plus, because you could get from either of the two roots the OR operation. Do you see that? So this
Yeah.
or that. So when this is OR operation, then you add. That is what I wanted to tell you. Simple as
Okay.
that. Okay. So 48 over 52 times 4 over 51. And operation means multiply. So we have and operation going like this. And when we have and operation, we are multiplying. Do you see this product? Correct?
Yeah.
Or operation, we are adding. Now, this particular tree can also help you answer some very difficult questions, which are called conditional probability.
Okay.
Conditional probability is, I'm telling you that I have drawn a card and I have seen that card. I'm telling you that this card is an ace. Now tell me what is the probability of getting an ace. You get the idea.
Yeah.
So in conditional probability, we are defining two events. Correct? So
Yeah.
event A and event B. Correct? And
Yeah.
based on these two events, we are trying to figure out the probability. For example, in this particular case, my question could be that I have drawn a card which is not an ace. Now tell me what is the probability of getting an ace. You get the idea.
Yeah.
As soon as I tell you that the drawn card is not an ace, so I'm already on this path. You get the idea.
Okay.
Correct. So now what happens is that my problem reduces to the domain of first draw, not an ace. So I'm
Okay.
only looking from here. And now if I say, what is the probability of getting an ace? So we know this is the probability of getting an ace. You get the idea.
Okay. Yeah.
So I will show you this concept in a very simple and easy way with the help
Okay.
of a dice.
Okay.
So I have actually introduced to you very important terms which are AND operation, OR operation, and the conditional operation. Right? That forms the base for multiple events. Clear?
Okay. Yeah.
Okay. Now, in case of a dice, I want to say that what is the probability of getting the sum as greater than, let us say, 9 if one of the dice is 6, if one of the dice is 6, you get the idea.
Yeah.
Now I know that when I threw, one of the dice was 6. Now I'm telling you what is the probability of getting the sum as 9 or more, greater than 9, 10, 11, 12, right? You get the
Yeah.
idea. Okay. Now, this type of a question can be solved very easily with the help of a matrix. So we have this matrix here. So we're talking about two dies. So let me write down. Let's say die 1 is red in color, let us say, and 1, 2, 3, 4, 5, 6 are its numbers. The other one is, let us say, green in color, and we get these numbers 1, 2, 3, 4, 5, 6. Correct. Now we are
Yeah.
saying that one of them is 6. And what is the sum? So the operation being performed is addition. So when you throw two dice, you get, let's say, 3 and 4, addition is 7. But 7 is less than 9. So it is not a success. Is that clear to you?
Okay.
But if I throw, I get a 9, it is not a success. I want more than 9. 10,
Okay.
11, 12 are the only three successes, right? Now,
Yeah.
in this particular case, if I do the addition, 1 plus 1 will be 2, and then I can actually go around and complete this table. Is that okay? Just adding the numbers, and I can actually complete the table, right? I'll just do it. It won't take much time. 5, 6,
Yeah.
7, 8, 9, 10. And that is how easy it is to actually make these tables. And it doesn't really take much time. Do you see that?
Yeah.
12. Now, I am looking for cases where I know one of them is 6. You see that? One of them is 6. That means I have restricted my domain to at least 1 6, correct?
Yeah.
So I will say, well, now that means for me what? It means one of them is 6. That is one possibility. That this one is 6, correct? The
Yeah.
other possibility is this, correct?
Yeah.
This could be 6. And now my domain has been restricted only to these numbers. How many are there? 1, 2, 3, 4, 5, 6,
6.
7, 8, 9, 10, 11. So that comes in the denominator. These are the total outcomes possible if one of the dice is 6. Is that clear to you?
Okay. Okay.
Now, what happens? I'm looking for a number which is more than 9. So out of these, more than 9 is what for us? Well, it is 10, 11, and 12. 10, 11, and 12. Do you see that?
Yeah.
How many? 1, 2, 3, 4, 5. So the probability of getting a number more than 9 is 5 out of 11. Do you see that part?
Yeah.
I have not used any formula for conditional probability to find the result. What I have used is a concept, and the concept is that by having an information, additional information, we kind of know the domain has reduced now to lesser number of
Yeah.
options. You get the idea.
Yeah.
So we have converged to a lesser number of options. Let us look only into those and get our result. That is what we are focusing on now. Is that okay?
Yeah.
Correct. Now, this question could be a tricky question also. It could say that if the first throw is a dice, let's say the green is a die, right? Correct?
Yeah.
Green is 6. First throw is 6. Then what is the probability of getting uh, this more than 9? You get the idea.
Yeah.
Correct. So in that case, if I restrict myself to, let us say, the information that I'm saying, when I say anyone, then it is open, right? This could be 6 or that could be 6. So we're looking into both the possibilities. But now if I'm saying that the red is, let me write down in red itself, that the red is 6. Same question. So when I say the red is 6, then I'm only looking into this domain. Do you get the idea?
Yeah.
And out of this, there are only 3 ways that I can get the sum as greater than 9. Is it okay?
Yeah. Okay.
So because those are the three numbers. So 1, 2, 3, 4, 5, 6. So it is out of 6, there are 3 ways. So 50% chances of my getting this. If first
Yeah.
is
Yeah.
6, then I
Okay.
know 50% chances of getting a number more than 9. You get the idea.
Okay.
So the whole story here is that we are restricting our domain to a limited region and then looking into only that part. Is that clear to you?
Yeah.
Correct?
Okay.
So that is how we have to look into probabilities, right? So we have also seen the role of table in this particular case, which you may say a matrix or a tree diagram, as we have seen here. And now we can look into Venn diagram.
Okay.
So in Venn diagram also, we could consider events which are 2 events or 3 events normally, right? More than that becomes too complicated. So Venn diagrams will consider when there are, let's say, 2 or 3 events, right?
Okay.
So one of the good type of a question here is uh, kind of like this. Let me make a Venn diagram here, right? And then we'll try to read the Venn diagram and see what information we can actually read from it. Is it okay?
Okay. Okay.
Let us say there are some students in your school and they have taken 3 subjects. Let's say physics, chemistry, and maths.
Okay.
Okay. So now let's put some numbers here. Let's say we have 3 students here, 1 there, 2 here. Let's say 5 here, 6 here, 7 here, and let's say 4 here. Okay. So we just made a Venn diagram. And when we write these numbers in these rings in the Venn diagram, can you tell me how many students are, and when we do it, and we also make a box here, we say, well, we are talking about all the students in the class. Some have taken this, but there are 10 who did not take physics, chemistry, or math. You get the idea.
Okay.
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 So that becomes the total set. So in Europe, they use this eta as the total set. We use union or we use S. It all depends from place to place what they are using as a total set, right? So
Yeah.
this is this total sample set. So
Yeah.
now from this information, first thing you have to tell me how many students are there.
Yeah.
Can you tell me? Because probability that number will come in the denominator, right?
Yeah. Yeah.
So
In
how many
total,
students?
yeah. In total, there's
Add
so
them all, right?
yeah, just add them all, and I think it's
Yeah.
just
So 10 plus 7
yeah.
plus 1 plus 2 plus 3,
Yeah.
add them all. You get the idea, right? 4, 5, 6 plus 4 plus 5 plus 6, right? Did I add them
Yeah.
all
Oh,
and get the number? What do you get?
38 when you add all of them.
38. So total number of students is 38. Now, how many take physics? P. So let me say, yeah, physics. Let's say NP. Let's call this as NP. Tell me. Only physics. So we'll add, physics is all of them, right? 10, 11, 13, correct?
Yeah.
And chemistry. We'll add all of them, right? 5, 5,
13.
10, and 1, 13 again. And then mathematics, right? So number in
16.
mathematics is what?
16.
16, right? So we get all these numbers right there, right? So we can now combine all these things. Definitely, if you add them separately, then what happens? 16 plus 13 plus 13 is how much? Add them all.
Yeah.
So
32.
6 and 6, 12, 42, right? So
Oh, yeah, 42.
we have 42 in all here and 10 less. 42 in all here, and you are saying here you included this 10 also, right?
Yeah. Yeah.
Correct. You included this 10 also, and there were only 38. So that means we are counting some students twice or thrice, correct?
Okay. Yeah.
So definitely we are counting some students twice or thrice, because what we notice here is that this group of 3 was added into everyone.
Yeah.
Correct? This was added to everyone. We have to definitely remove it, right? Similarly, if you see this combination, it is again added, right?
Yeah.
So, so there is a principle of inclusion and exclusion which comes into picture. So we'll write down principle of inclusion and exclusion. So that is very important. So normally what will happen is that they will tell you that in a group of students, some students took physics, some took chemistry, some took mathematics, some took physics and mathematics, some took physics and chemistry, some different combinations. You get the idea.
Yeah.
All these numbers will be given to you in a paragraph. Perfect. So if those numbers are given to you in a paragraph, you have to start from inside out.
Okay.
Inside out means we have to look for a statement which says all the 3 subjects, physics, chemistry, and math, 3 students took, correct? So once you know that 3 students took physics, chemistry, and math, then you put in 3 here first, correct?
Yeah.
Then you know out of 13, 3 are already allocated. Then we have to
Yeah.
look into the combination of 2. How many in physics and maths? Let us say in physics and maths, there were 5 students. So 2 remaining will go here. Do you see that? So 3 plus 2 is common to both maths and physics. So if the next statement is that the number of students taking both maths and physics are 5, then 3 have been allocated as all and plus 2 for physics. You get the idea.
Okay.
So
Okay.
if you start from inside out from the given information, which will be like a lot of information here, you will be in a position to complete the Venn diagram, correct?
Okay. Okay.
Once you have completed the Venn diagram, after that, you can answer so many questions based on probability. That if you pick a student at random, what is the probability that the chosen student has taken both physics and chemistry, for example, right?
Yeah.
So those type of questions now can be answered. We could even make it more complicated and say the students which have not taken chemistry but has taken physics and mathematics. You get the idea.
Yeah.
So we could now combine the probability questions with these 3 events using complement of 1, complement of set of 2, right? So we could say or physics or chemistry and this. You see that using
Yeah.
these basic operations, we could complicate our case, but if you have a clear cut Venn diagram, very easily you can answer all these questions, correct? So making correctly a Venn diagram is also a good exercise, and the key here is start from inside out.
Yeah.
Correct. So if you start from inside out, you are going to get the right results.
Okay.
So basic probability principles we have done today, you have understood. In the next class, I will actually introduce to you 2 very powerful tools. These are permutation and combination. So
Okay.
permutation and combination helps you to do counting of numbers possible in many different ways and very easily and fast. You get the idea. So
Yeah.
we'll look into permutation and combination in our next class. Once we
Yeah.
have this foundation, then we will start answering questions based on probability. Correct?
Okay. Yeah.
So today, do you get an idea of what probability is and what are the terms which are normally used? Can you summarize some of these?
Yeah. So basically, like today, like we just went over like basic probability, and like you like using Venn diagrams and tree diagrams as like a way to like outline them and show like how it's gonna look like. And yeah, so I'm still like I understand to like a good extent. I'm just like a little bit like confused still on like the tree diagrams because it's
Okay.
like more like, so if we could just quickly go over that, then like that'd be good.
I'll
Like
give
'cause
you a
that,
minute. Within a minute, we'll go through it. Very simple tree diagram. It's not difficult
yeah,
at all.
yeah,
And
it's just yeah,
it is easy. And you should be very clear about it because sometimes the question is very difficult. For example, I'll give you a difficult question just now. When we toss a coin, we say it is a fair coin, correct? So
yeah,
fair coin means you get a head or a tail, and the probability of getting head or a tail is 50-50, correct? 50%, right? If it
yeah.
is a fair. But now I'm saying it is unfair coin.
Okay,
We say biased. And I'm saying it is biased so that you get more heads. So probability of getting head is 60% and probability of getting tail is 40%. Do you see that?
okay,
So all of a sudden I've changed my question. When it was 50-50, it was a very easy question to work with, right?
yeah,
So we toss it first time and the probability of head is this. Now again, we toss it again. So again, when you toss it, then probability is you may get head or you may get tail. Similarly, here also you may get head or you may get tail, right?
okay,
Now, since the coin is the same coin, probability of getting head will be 60%, probability of getting tail will be 40%, correct?
okay,
So we again get 60-40 ratio. Is that clear?
yeah, yeah. I understand.
Now, my question is, in this particular case, what is the probability of getting one head, one tail? It could be order, could be different, right? So,
Yeah,
in this way, we get two heads, correct? In this way, this tree path, when you follow, you get head and a tail, and this path gives you tail and a head, and this part gets you tails. You get the idea.
okay, okay,
So, my question is, what is the probability of getting a combination of head and a tail? Well, when you multiply these, you get getting two heads is 0.6 times 0.6, correct?
yeah,
And coming to this part is 0.6 times 0.4. You just complete this table, and this is also 0.4 times 0.6, and this is 0.4 times 0.4. Is that clear to you?
yeah,
Correct. Then the probability of getting this is multiply these two and add, right? So basically, it is 2 times 0.6 times 0.4. Is that clear to you?
okay,
6 times 4 is 24 times 2, 48. So it is 48%. Is that clear to you?
yeah,
So it becomes 48% of getting two heads, correct? The
yeah,
same question could be, what is the probability of getting another very important term is at least one tail. At
yeah,
least one tail. So when I say at least one tail, then which all qualify? This qualify, and that also qualify. Do you see that? At
yeah,
least one tail. One of them is tail. Both can be tail.
okay,
So you can add all the three of them. You could also work with a complement. Complement means one minus both heads, right?
yeah,
One minus no tail. Do you understand? So complement of a function could be faster since we are only looking at this now and we are saying 1 minus 0.36, correct?
yeah,
Is my answer for at least one tail. You get the idea. So same
okay,
question, we are approaching with a different logic, but we are arriving at the right result. Now, for such a question, where you're looking for a coin being flipped, especially biased coin being flipped, tree diagram is a very powerful tool, correct? You see that?
yeah,
And if I move to the third level, well, that is it. Up to the third level, this is one of the best ways of answering such questions,
okay.
right? Now, is the tree diagram clear to you?
Yeah, yeah, yeah. I understand it now. I think I was just overthinking it, like
Okay, yeah,
kind
it's
of.
very simple. It's probably simplest. And it is a preferred approach if it can be applied.
Okay.
If it can be applied, right? You get the
Yeah.
idea. Then you should use this first preference. Okay. Okay,
Yeah.
then we'll end our class here today. Okay.
Okay.
Great.
Okay.
Thank you. And all
Okay.
the best.
Thank you very much. Have a good night.